So when we left off last time, we had made it part of the way through lecture 18, and we came across a couple of interesting things. One of them was this claim that we can spread numbers out in space with cyclical redundancy check. And I wanted to take a stab at trying to draw maybe a little bit of what that might look like. So if you can detect simple errors with a parity check, then if I use each of these circles to represent a possible string, then these red circles in particular surrounding the blue one in the center represent bit errors at some given bit position. Maybe if it's 8 bits, then there's going to be 8 of these circles, each one of which represents one of the error combinations, and your parity is going to catch it. It's going to catch it in the act because it won't match up correctly. So the problem is if you flip a bit and then you flip it again, like a 1 to a 0 and then to a 1, or you flip a 1 0 to a 0 1, things like that, then you end up getting different combinations that you and I both know are invalid, but which this scheme will think are valid because there's not enough distance between here and here. So if you're really convinced that only the worst error for all practical purposes that's ever going to hit you in this scheme is 1 bit error, then you're completely protected because your parity will catch every one of these. So any error that changes your good string into one of these bad strings will get detected. The problem with transmission networks is that's not realistic at all. You can have tons of bits that get changed, and what you're worried about are ones that get changed and maybe the CRC or the error code gets changed as well, but it's easy to come up with another valid string. So you remember I did the division by 10? What if you take your string and you divide it by 10 and treat it as an integer, divide it by 10, the whole packet gets treated as some big giant integer. You divide it by 10, and you're going to get a remainder, and you send the remainder along. And because I also know you're using 10 as a generator, I'm going to divide this long, thousands of bit long integer by 10, and I'm going to see if I get the same remainder. Well, there are millions of combinations of errors that will have the same ratio, the same remainder that your good one did. And so it's impossible to detect whether it's good because the generator is not large enough. The more distance you put, the larger the generator you use, the more distance you're going to put between things. And so what that is basically going to mean is these guys are all going to be marked as frauds as well. In fact, you're going to have to go way out to here to find another valid string. And therefore, anything that happens in this area is not going to fool anyone. They're going to get caught as errors. They'll calculate the number, they'll divide it by the generator you've agreed on, they'll come up with the remainder, and it will not match. So either the remainder got changed or the contents of the packet got changed, but you're out of here. Third strike, you're out. Right? So that's kind of the idea of using number space separation to create more resiliency in your numbers. And that's one way to look at what a cyclical redundancy check does. There's lots of good stuff out there on CRCs if you want to look at them. Okay, one of the most fundamental things you got to remember when dealing with data networks and the internet in particular that makes them different is the things that don't make them different. They're all using the same types of physical circuits and fiber and airwaves and frequencies and copper cables and distances between continents, and none of that stuff's different for any type of network. That stuff's all the same. What makes, and also we can go a little further, and say that the way you encode ones and zeros might not be any different. So we could exclude from data networks that are encoding data, but they just happen to be using ones and zeros. Those are just digital networks. They're not sending these packets of data around. And the reason that we got pushed to doing packets of data is because we needed devices along the way to be able to look at packets coming from a location maybe that they weren't expecting before, which won't happen on just a digital network, right? And the reason why that might be happening is maybe their link went down. And think back to the beginning of what one of the motivators was of trying to survive an attack. So you needed to divide your data up into this envelope and put enough addressing on the front of it and teach your devices how to interpret it so that any packet at any time can show up from any place on the planet going to any place on the planet, and your router will have a decent idea of what to do with it, of where to send it. It's really quite remarkable. So what's the difference then? It's that they're shared. That's what causes us to have to do this. If you have a redundant connection, but you're not sharing it with anybody else, then why would you switch them to packets from just streams of ones and zeros? Do you change the protocol your computer uses to talk to your printer just because the USB cable had to be replaced? No, it's just a redundant connection. Doesn't make any difference at all. So shared is the key driver for all of this protocol stack, all the layering, the addressing, and dividing up this string of data into these smaller chunks called packets, or whatever other acronym, what other name you want to use. So there's basically different kinds of links. There are links that go from one specific point to another, and that is all telecommunications links in the world: dial-up lines, ADSL, T1s. All of those are point-to-point links. They may bundle those up and give them to you as something different, but that's the fundamental building block. The other type of link you have is one where multiple people can share it at the same time. Think of radio waves, like cell phone connections or Wi-Fi, or even cabled systems where multiple people connect to it at the same time, like your water system or your gas system or your electric system. Those are all shared networks. You're consuming something other than bits, but there's different rules of behavior, different dynamics that come from it being shared with somebody else. You want a high enough water pressure in a water system, you got to make sure you have enough pumps in there to turn on if 5 people decide to turn on their water at the same time. As a completely non sequitur interesting fact, the day in the New York water system's history when they had the most water processed and the most sewage treatment sort of spike in usage was after, at the time anyway, after the last episode of MASH, after 20 years when it finally aired. Everybody watched it till the end and then ran to the restroom. It's like, hey, you can't regulate biology. So old-fashioned Ethernet falls into that second category. All right, let me see if I can get this thing to deselect this. So multiple access protocols are ones that you design because they're going to be on a shared channel. 2 or more people could possibly transmit at the same time. If they do, you're going to declare that a collision has happened, and you're going to kind of design your system around it. So Ethernet is a multiple access protocol, and that is why you have a multiple access, or MAC address. That's where MAC address comes from. You're going to have some sort of algorithm that will determine what part of the network you can get. It will regulate things like how big frames can be, how often you can send them, when it's your turn to send them, what you do if there's a problem, how long do you need to wait before you try again, etc. So what's different about this type of network than a lot of the communication networks used in the telecommunications industry is that the messages that go back and forth to control what's going on, like set up this channel, ring this number, here's the phone number they typed, all of that kind of stuff is sent along the same channel as the data. So, you would hear it if you had a way to listen. There's no separate channel outside of what you're trying to communicate that's just used to control things, an out-of-band channel for coordination, in other words. All right, so we're going to have to get pretty good at dealing with this on a per station basis. So let's say you have a broadcast channel at a certain bit per second rate. When one node wants to transmit, it can do so. When N nodes want to transmit, they have to share it, fully decentralized. no centralized node. That would be awesome if we could come up with something where we didn't have to have a central box. In fact, that was a huge motivator for Ethernet, was not having to connect all of your terminals, all of your screens and keyboards to some central communication hub sold at a very high price by IBM, as well as the devices at the edge that you're having to use. And it said, come up with something where everybody can just kind of share on a wire and figure out when it's their turn to send. Try it. If they interrupt with each other, then sorry, they'll back off. So this is a conversation you're having at the dinner table between 4 or 5 people, trying not to talk over each other, as opposed to being in a conference where there's 1,000 people, but there's someone in charge of calling on the next person. I think there's a person over there. Can you take the microphone back to them? Just wait for the mic, sir. Okay, you can ask your question. Right? That is not a decentralized control mechanism. That's one where there's still a central access. So we didn't want that with Ethernet. So there's 3 broad ways of designing a system where people share the network. One of them is you divide the thing into time slots or frequencies, or give people different prefixes to use, and you give each of them their very own slice, whether they're there or not, whether they're using it at the time or not, whether they need more. And people next to them aren't using theirs, too bad. You have a fixed constant amount of bandwidth that you're going to be allocated, and that's all you're going to be able to use. So I will at least be able to give you a small piece which I can allocate for your exclusive use. Okay, sorry, I had to cough. I hope that muted. The other way of doing this is random access, where you let just people try, and maybe you tell them, listen first before you start to talk. But that's not going to be perfect. It takes time for people to hear what you're saying, and so you could have listened and it's empty, but in fact somebody at the other end was sending something at the same time. So that's a collision. You've got to figure out a way to recover from collisions if you want to do it this way. The big advantage here is, as long as it sounds like it's empty, you can send a batch of data. Right? The other way to do it is taking turns, but if you don't have something, then maybe somebody else can get an extra turn sooner. But that requires some sort of coordination among everybody, and it's expensive. So let's take a look at each of these. The first one was channel partitioning, and this is one where I divide up slots. So one way of doing that is to divide up time spaces. And in this diagram, what I'm showing you is given the orange person time slot 1, the red person's 3, and the blue person 4. This is the way the telephone network was designed. You have a T1 carrier. It has 24 time slots in it. You can transmit 8,000 of those packets, 8,000 of those chunks of 24 slots a second. Each person gets 8 bits in there. It's just a fairly small amount of data to send, but that's 64 KB per second. That's enough to digitize and transmit a phone call. So you can send 24 phone calls at a time with the device, because that's as many as we could figure out how to cram in there at a time. And so that's been around since, in practice, working for customers since the early 1970s. Hartford Insurance was the first one to get a T1 line in the world, outside of a lab. All right, so this is one where we do rounds. Disadvantage of this is you can't use somebody else's rounds easily. The other way to do it is divide up frequencies, and this is called frequency division multiplexing, or multiple access, FDMA. And this is one where I'll let you use it all the time, but only for a narrow frequency of it. So I have a coaxial cable that brings my cable television channel to my house, my system to my house, and it has hundreds of channels on it. In the old days, you would just frequency shift them up or down so they could occupy different ranges on the cable, and we all watch it on one frequency range, and so they'd just get moved back down again to kind of undo what you did. So this one, you get a constant stream, but it's small. And again, it's not obvious how you're going to use somebody else's frequency range if you do that. This one, when you have to send something, you can send it at the full data rate. With random access protocols, the third one, then this is the one where you've got to be a lot smarter. So not everybody cares because they don't have things to send. But when you do have something to send, you could, presumably have the whole thing to yourself. Maybe you don't let people send for very long because you don't want them to hog up too much of it. You want to give other people a turn. But, they can stop and send a big packet and wait a moment. And if it's still empty, do it again. And maybe they have a little courtesy time they're supposed to wait to give somebody else a chance and then do it again. And you can send something at the full rate of the network. So you can get a huge file across quickly this way. If you do detect a collision, then you're going to have to recover from it. So the protocol specifies that. There's some good examples of this. One of them came from the University of Hawaii network, and it's one called Project Aloha, and it's easy to find references to this out here. And it's still got some stuff up, I think. I don't know that that really is, no, that's a little different one. Let me see if I can find this. That looks like a worthwhile project as well, but see if we can find this. Aloha Net. There you go. And will they mention the players in here? Norm Abramson. There he is right there. Looks like a nice guy, doesn't he? He's the one that developed this concept. And Aloha Net is famous because it gave us the idea for how to do Ethernet. And so it changed the world. What they had in Hawaii were a bunch of campuses separated by islands. Sending cables under the ocean to go between them was completely impractical. It was expensive. It's done, but I mean, it's not like you're running it across the bottom of a pond. It's thousands of feet down to the bottom of the ocean because these islands are like the top of volcanoes that took a long time to build. So it's a really long cable, maybe too long to build lots of kinds of networks. So they used radios, definitely the shortest path. But the problem is, how do you keep people being polite? In other words, do you send each from a central location, send out some beacon that all the campuses can hear at all their receiving stations around the islands, some of them close by, some of them far away, and you say, okay, everybody, quiet. I'm going to give Station 3 a chance to send something, and then Station 3 gets to send you something, or you get to send something back, and then it goes to Station 4 and 5, or maybe you let people request if they've got something, some other scheme to get it done. So that's one way to do it, but that requires coordination. And you also can try to just be courteous and listen to see if the network is empty or not. And so 3 can listen for a moment, and if it doesn't hear anybody else sending something, then it will assume the network is available. And after all, these guys are all using radios, and the radio is strong, and so it can make its way from this island to this island. So if you are in the middle of sending something, he will be able to hear it if he listens for just a moment. The problem with that is different frequency spectra are good at getting through air and not getting through Earth, and vice versa. And there happen to be a few giant mountains separating these campuses. So on one of the big islands, you've got a campus over on this side, and you've got your campus on this side. Both of you have little radio towers, but you can't hear each other, no matter how hard you listen, because the volcano absorbs the energy. So you will end up conflicting with someone, whether you try to or not. So what you're going to do is listen for, you'll send your message, and then you'll listen for an acknowledgement back. And if you don't get one back, then you assume that something happened. You'll wait a moment and try again. But what doesn't make sense if this happens is for everybody to wait, as soon as they get the timer goes off saying I didn't get the act, to just try all at the same time, because you're just going to doom yourself to have another collision over and over and over. So there's some randomness built into this. And what you'll do if there's a collision is you will rate a random amount of time between certain range, within a certain range, and it's unlikely that the other person will pick the same random amount of time. And so one of you will start first, and the other of you will hear it and go, okay, well, stop my random timer. It's too late. I waited too long. Somebody else got the network. and then you wait until it's idle again, and you'll roll a random number and try again. So this idea of random backoff is fundamental to the way these networks work. So not only are you accessing it at any given random time, but you're going to recover from the collisions via delayed, randomly delayed retransmissions. That's the genius that made this thing, made Aloha work in particular. So with slotted Aloha, all frames were the same size. You had kind of a heartbeat signal that came out from Honolulu, and it told everybody, if you have something to send it at the start of one of these heartbeats. So it would make it easy to know if you were able to detect something, because it would be when that heartbeat. If you didn't hear something, then maybe you can start. It also makes it easy for the receiver to know kind of where the beginning and the end of your packet is, because you're giving them a signal that tells them that. So nodes will transmit only at the beginning of a slot. They're all synchronized. If two or more send at the same time, that's a collision. When you get a slot, you'll transmit it. Sorry, when you get a frame from your application, it says, hey, send this for me. You will send it in the next slot that's available. Just try it. If there is no collision, great. If there was a collision, back off some and try it again. So in this example here, you're not even listening to see if the network is available. And with slotted, how could you, right? So if you say, this is the time I have to send something, and if I am, I'm going to send it to here and send it to here, etc. If you listen here and you don't hear anything, you've already missed your start time, and somebody else may have started sending. So with slotted Aloha, everybody gets this pulse, this heartbeat that says, coming up now is the start of another packet, and you'll just try. You'll just try and see what happens. All right, so here's an example. 3 nodes all try to send at the same time. It's a collision. The first guy rolls a random number 2. The second one rolls a random number 2. The third one rolls a random number 1, 2, 3, 4, 5. Nobody rolls to wait 1 more. So nothing happens the next slot. Just chance, but that's an empty slot and it's inefficient. On the third slot, this is when 1 and 2 had said, I'm going to try again. And they both try again, and they collide again. They don't know who they're colliding with. It's just a combination of electrical signals. It's just like garbage. And so they know they've had a problem, so they roll random numbers. This time 1 rolls a 3 and 2 rolls a 1. And they go to the next slot. 2 transmits, happens to be the only one. Success. Fourth slot, nobody transmit, wasted slot. Fifth slot, 1 and 3 try. They roll again. They finally make their way through this. It's crazy simple, and it works great as long as you're okay with only using about 1/3 of your network capacity. So get yourself lots of radio, and you're going to throw a lot of it away, but it's dirt cheap to implement. And you can go through the probabilities, but if you've got a node that has success in a slot, then that, if he's got something to send, the probability that he sends it is the transmission that he transmitted during that time and that everyone else did not. So if at any given moment somebody has a 10% likelihood of transmitting a frame, then in order for it to be successful, you will have to hit on one of your 10% of the times when you send something, simultaneous when all other 9 people have 1 minus 10, 90% of the time when they are not sending something. And those probabilities all multiply together, which is why you see this exponent in here as well. Okay, so not very efficient, but works. Then they figured out, well, we could make it unslotted Aloha and even make it simpler. The difference here, instead of having a heartbeat to tell you when to start, just listen for a moment. So I go back to my example. Here I listen for a moment and I don't hear anybody, but it's not associated with like when you're supposed to start. There's no more heartbeat anymore. So you'll listen for a minute and you'll send. Maybe you started listening here or here. So you don't have to wait for the next heartbeat. You can start sending at any moment you have a frame as long as you listen for a moment. Now you're still going to have collisions, especially with people that you can't hear, but it will cut down on a lot of them, because instead of everybody just randomly trying the start of a slot and you have no idea who's going to show up that day to send something on that time slot, Now you're going to listen, and you're going to catch most of the time detecting when the network is busy. And so you'll have fewer collisions, but you'll still have some because you can't hear everybody else. So no synchronization. When a frame arrives, transmit it immediately. In this case, because you did not listen, we didn't add that innovation, you just bull-headed your way onto the network, barged ahead. Your probability of collision in this version will increase, but to fix that, just listen for a moment at first. For pure Aloha, this one's even less efficient than the other one. But the good news is that radio transmitters were getting better and cheaper, and so they were more than able to overcome this by putting in wireless networks that had much higher communication speeds. Right? All right, so what we do with Ethernet is that extra little step that I hinted at a minute ago. We're actually going to listen to see if the network's busy first, and that's called sensing to see if you can hear the base sinusoidal carrier wave that indicates that the network is on, you are connected to it, and no one is perturbating that wave, changing the shape of it to try to encode ones or zeros. That's how they would do it. So if you're 100 megabits per second, you've got a wave out here, then you figured out a way to change the shape of this thing so it means something. So maybe this is 1001111, who knows, right? So you'll sense whether the carrier is available, and you're going to be mindful that there's multiple people accessing it, and therefore you will hopefully avoid lots of the collisions. If the channel is idle, send it. If it's busy, don't. So this is like don't interrupt somebody else. If you hear somebody else talking, don't start talking to them over it, or it'll be possibly considered rude. So there's a famous way of drawing this as a timeline diagram. And I don't love the way exactly the book did it, but we'll show some more detail. So what this shows is a network left to right with 4 computers on it. We can call them 1, 2, 3, 4 if you want to. And time goes down the page. And at time 0, one of the computers starts to send something. And with every passing nanosecond, you go down this chart, and the bits that you've encoded on your medium reach further and further away. They propagate at close to the speed of light across the network in both directions so that other computers can hear it. That's how they sense that you're sending something. So that's great. Normally, if you send something like that, it'll make its way to all the other computers and everybody's happy. But a collision can happen while doing this because it takes time for your signal, even at the speed we're talking about, it's significant amount of time for your signal to reach, let's say in this example, the last computer on this network. And so when he listens at time 1, you've been sending since T0, but none of your signal near the speed of light has been able to make it to the 4th workstation, and so he thinks the network is free also. And for all you know, how do you know you didn't just clobber somebody when you started to send? Who died and made you king? So T1 is the time where we have another transmission. These 2 signals will combine to form a different electrical signal at that point where the yellow and the red meet. At that point, there's been a collision, but no one knows it yet. It's not like it travels at a different speed than the other stuff did. What happens is these 2 sine waves combine to form a new sine wave. No problem whatsoever with doing that. But what you hope is that you've designed your transmission protocol and defined exactly how ones and zeros are defined and in what combinations and patterns they can appear, that this change that results from these 2 signals combining will result in something that you will immediately recognize as invalid. That's the prayer. So this begins to propagate its way back across the network at the same speed it came, and it's not until you get down to this time here. Let me draw a line on here. It's not until basically this time here where those lines intersect that the original computer hears what's going on. And he's still sending, so what he'll notice is that what he's putting on the wire doesn't match what he's hearing on the wire. So you have one of these systems as well. You have a mouth and an ear. And if you ever put on headphones or something and people tell you, like you're talking really loud, it's because you've lost your feedback. So you know you're constantly monitoring what you're saying, whether you realize it or not, by hearing your own voice. That's why with these headsets I'm wearing, one of the things that these headsets do is pump my own audio back into my ears so I can hear it along with anything else it's bringing in over the network for me. So it takes a little while for you to detect a collision. This computer will actually detect it first, but he'll just think like it's gibberish. He won't think, oh, somebody's collided with me, because this wasn't sent by him. It may be for him, destined for him. He may be the target, but he'll figure out that it's just garbage and ignore it. This sender will then be the next one to detect it, and then the yellow sender will detect it, and the last person to figure out what's going on is going to be this guy at the end. So this collision has taken place. This transmission time has been wasted. You want to make sure that you give this a chance to clear off the network and back off a random amount of time and try it again, so as you do not doom yourself to repeating it over and over and over again. So it shows a little more of the diagram, and that's the part that I think is wrong, drawing the colors again at the bottom. So CSMA-CD is a variation of CSMA. It stands for Carrier Sense Multiple Access with Collision Detection. Within some short period of time, and as soon as you detect one, you stop using the medium so that you preserve bandwidth for getting other stuff done. There's no point in continuing on singing the rest of the song if somebody is singing on top of you at the same time. So collision detection is easy on wired networks. It's tough as nails on wireless networks, and we'll see why. So collision detection, these two guys figured out what was going on, and they gave themselves a little bit of time to send out a signal to let everybody know, hey, forget about that packet, just in case somebody managed to receive enough of it. And the way Ethernet does this is the network interface card gets a packet from above. It gets a datagram from the network layer from IP. It creates an Ethernet frame. It listens on the network. If there's nobody sending anything, it immediately begins transmitting the frame. And it listens the whole time. Every bit it encodes on the wire, it is listening to see with its ear if that's what it's hearing. If it ever detects a perturbation that's big enough that it believes it would prevent the other person from correctly interpreting what it was trying to send, it will declare that a collision. It can be with another user. It can be with a motor or a passing airplane that generates frequencies. It can be lots of sources. A microwave oven will interfere with Wi-Fi, cordless phone, etc. If it transmits the frame and it hears the whole thing, it's good to go. It's clean, right? It's done with that frame. If it senses something else happening while it is transmitting, it will stop trying to send. It will send a very obvious signal to make it perfectly clear to everyone, like bad packet. And then it will enter this exponential back-off mode. And what this back-off mode does is waits a small random amount of time. There may be another collision. It may or may not be with the same person you collided with before. It could be with somebody new that just showed up. And if it happens again, if you have another missed attempt to send your frame, you will back off. You'll increase the size of your random window, of your time window, and you will pick another random time within there. And then if that happens again, you'll double the size of that window again and pick a random time in there. And so this is called exponential backoff. And after 15 rounds or so, your network card's going to say, you're not going to be sending anything today. There's no network here anymore. And so the network's been lost. Okay, so the efficiency of this, if there's delay between two nodes for the bits to get across the wire once you've encoded them, and this is the time to actually encode the frame size, then your efficiency is 1 over 5 times the propagation delay divided by the transmission delay. So as the propagation delay goes to 0, then this ratio adds nothing to the formula, and therefore this gets closer and closer to 1 over 1, and that's perfect efficiency. The other way to do it is no matter how long the network is, if you're able to transmit like crazy fast and this goes towards infinity, then it also makes this ratio worthless when added to 1, and you are at 1 over 1 again here anyway. Right? So better than Aloha and cheap. So that's kind of the idea. All right. With Mac, you can take turns, but it's not common. We usually use random access. And channel partitioning, you could do something like that. You can choose to divide it up that way, but we use random access to do it. Taking turns is another way to do it, back and forth. Maybe that's like the best of both worlds. And there have been technologies that do all of these. Here's an example of one that's sort of the master slave. It tells each person, it's your turn to send something if you have. Some IBM systems work this way. Do you have something? Yes. If so, send me data. Okay. Another one is round robin. You're going to pass this special pattern around. Network cards are listening for this pattern. If they see the pattern, they know that it represents it's your turn to send something if you want. And if you do, behind that pattern, you will change that pattern a little bit before repeating it to let the next person know there's a payload here. You'll put who it's for, and then you'll follow it with all the bits of your with your payload. All right. So this one passes around, nothing to send. This one has something to send. It gets attached, and it moves on. Cable access networks are typically shared networks for data, and you are going to slow down as more people come home because of the competition for the local region, the local part of your town. These are called last mile networks, the very last part before it gets to you. That's one reason why rush hour on the internet can make things slow. Another reason could be because the backbone's overwhelmed. And it doesn't matter what technology you're using at the edge, you're never going to get more across the middle because it's not in the last mile. But this is really focused on what we can do to make the last mile more efficient. So what cable access networks will typically do is take some of the television stations off the air and give that bandwidth over to be used for data. And you'll have a variety of multiple 40 megabit downstream channels and some 30 meg upstream channels. And you usually want as much up and down if you're a business, with as much likelihood of sending things as receiving. That assumes you have things people want to get to, like your own web server in your office. But most of us send very little up to the network compared to what we get back from the network. It's massively different. So upstream, downstream channels, there is a standard for this called DOCSIS, and this basically uses frequency division upstream and down. There is a time division version of this as well that's out there. So just to kind of summarize this section that we just went over, we have multiple access protocols. They divide up the medium for people to use. That's one way of doing it, channel partitioning. Random access, we saw several different versions of that we can use. Some of them are inexpensive and easy. Some of them are a little bit harder. But CSMA-CD is what's used in Ethernet, collision detection. It's much harder to detect a collision on a wireless network. So what we try to do there is just avoid them, add some extra permission asks and may I and things like that to reduce the chance that there's going to be a collision. So that's called collision avoidance. And then there's taking turns at the end that we looked at. All right, very good. We made it through that lecture. Let's plow ahead and get a little further into this. So we have a good amount of time left. However, we are back to the competing daylight saving times in the two countries. So we're back to this lecture ending a little earlier than the Monday one did. So we'll end in 19 minutes. All right, speaking of 19, lecture 19. What we're going to take a peek at now that we've seen some of the basics of this is how we actually get some of the nuts and bolts, packets and frames across these wires on particularly Ethernet. That's the example that we'll mostly use. So for a multiple access address on an Ethernet network, we give every device its own unique address. So when it sends something, there's no question about whether it was them or someone else. But what's really curious about these MAC addresses is they are globally unique, but you can never see more than the few that are on your local LAN. It's impossible for you to see any others. But the reason why we still give you a globally unique address is because unlike with IP where we can change your assignment every time, we hard code this one into your hardware. And just in case you show up on a LAN with someone else that has the same randomly assigned MAC address, which we could do, then you have a big issue. So instead of suffering that fate, and also to increase some knowledge and security of what's going on, we actually manufacture your MAC address into your system. And I can see what mine is. I'll open up my network preferences. Here it is. And I'll go to Ethernet and go to Advanced Settings and look at the hardware. And there is my 32-bit address, basically. And the first 3 bytes are assigned to the manufacturer, and then they assign all the combinations of the last 3 bytes worth of bits out to their devices. So it's quite a huge number. It's less likely to happen than you think. This particular type of MAC address is 48 bits, and that's mostly what we actually use these days. So that's for Ethernet. And if I switch over to my Wi-Fi connection, it's not active, but it's still going to have a hardware address. This one is, ends in C7, and I just talked right through the other one. It may use the same one. No, it doesn't. See, it has a different hardware address for Ethernet than it does for MAC, and I'm hoping it would. So the IEEE, the Institute of Electrical and Electronics Engineers, the same people that keep track of the Ethernet standard and the Wi-Fi standard and all of those others, they are the ones that rent out MAC addresses, sell blocks of MAC addresses. And you can look them up. So I'm going to, one more time, this time with feeling, I'm going to go grab my MAC address, copy it to my clipboard, go over to my browser and say, look up MAC address. And I misspelled it, but hopefully Google will fix it. MAC and OIU lookup. This one's a good site. So you can put the company name in, you can put just the first part of the MAC address in, or the whole thing on some sites. This one only wants the first 6. So these are talking about hexadecimal digits, each of which represents 4 bits. So there's 1 byte here, 1 byte here, 1 byte here. It's 3 bytes total. Okay, and it's assigned to Apple. That's who's got that one, right? And that makes sense because you guys know that's what I use. So I use a Mac. So we don't think we're going to run out of MAC addresses for a couple of reasons, because we can reuse them based on each LAN technology. So they can be reused on the same computer many times or around the world many times, whether people every time you change the layer 2 technology from Wi-Fi to 100 megabit to 10 meg to some other type of cabling technology, you can reuse the thing over and over. The other reason why we don't think we'll run out is because the odds of you ending up on a LAN with somebody with the same MAC address is extremely low. And if it happens, assign yourself another random one right then on the spot. You have to change your operating system so it'll allow you to do that, but it's no big deal. It could complicate your life a little bit because one security mechanism we use is we teach devices like Wi-Fi routers or network routers to only allow packets that come by from these following hardware addresses because these are known hardware devices. Okay, so that's a little bit about how that works. So it would mess that up a little bit, but we don't think we're going to run out of stuff. Right? Every adapter on a LAN, in other words, every place where a cable plugs in, the thing the cable plugs into has an Ethernet module running unless it's designed especially to avoid it. So On this picture, I have 4 devices, 4 laptops. What I don't show in the middle is that there's an Ethernet switch into which all 4 plug. So there's 8 instantiations of Ethernet on this diagram. 8 times somebody had to go and buy a chip that knows how to do Ethernet and add it to one of these devices. Those chips are cheap, and we may have looked at these before. Broadcom Ethernet chip. Let's see if I can find. Normally I just pull up a whole row of images from this, so I must be using the different thing. So these things, these are all Ethernet cards with Broadcom on them, but you can buy Ethernet on a chip directly from people that make that, what's called merchant silicon. It's just kind of widely available. And that's what you see here. Oh, this is kind of cool. There's some interesting old stuff in here. That's quite antique, I think. All right, back over to where we were. So each of these devices here shows that it has a MAC address. One of the things that you might do with the switch is hide the fact that you're got a MAC address by just making sure you never ever send anything with your address on it. And the way you learn where people are is you just watch for the MAC addresses to go flying by. Every time someone sends something, that someone's address is on it as a source, and you know exactly which cable they came on. So now you know where they are. You look at where packets are coming from. All right, more on LAN addresses. It's managed by the IEEE. There's a fairly large address space. It's completely portable. You can move from one LAN to the other. IP addresses change when you move from one spot to the other. Your hardware address does not. So if I have a packet and I need to send it to another computer on my network, what I show in this diagram is I've added a second type of address. Each of these devices now has the original hardware address, the MAC address, the Ethernet address that they had before. That's what this long 48-bit number is, 6 bytes, 12 hex characters. But it also has an IP address. And when I'm sending packets from my browser and stuff, I'm sending things to IP addresses. I'm not sending things to hardware addresses. I don't know what somebody else's hardware address is. So if I'm trying to reach google.com, what I'm going to do is broadcast a request on my local LAN, and it's going to say, excuse me everyone, may I have your attention please? Then I want to reach this IP address. Is there any device on this network who would be willing to help me? If so, please respond with your hardware address, and I will send an Ethernet frame your way for you to look at and hopefully help me forward. So that's an attempt to figure out which hardware addressed device can help you reach a certain destination IP address. And there's a protocol to do this called Address Resolution Protocol, or just ARP, as we universally refer to it. So what ARP does is build a table where you learn over time where devices are by just looking at where things come from. You know, if you see somebody coming over this hill and they tell you they're from Tulsa, Oklahoma, then you know if you need to send something to Tulsa, Oklahoma, go over that hill. And if you see them coming up the alleyway and they tell you they're from San Antonio, then you know if you need to send something to San Antonio, send it that way. So it's where they're coming from that causes you to learn where people are, not where they're going to. Until you see something come from there, you have no idea that that's where it is. And how could you help someone send something until you've seen something come? Well, computers, fortunately, are really chatty. And so all you have to do is listen for a minute, and you'll build yourself up a table of these entries just by watching all the garbage go around. Like there's always idle chatter on a LAN. So you'll add an entry every time you find someone. You're not going to keep it there forever, because maybe they move, maybe they found a different way to get here from Tulsa that doesn't require going over that mountain. And you'll flush it out periodically and kind of relearn to make sure you're getting the best data. And so that is a time to live. And in this book, it says it's typically 20 minutes. All right, so again, hardware addresses are things that you see only on your local LAN. You will never see hardware addresses on any other LAN other than the one you are currently connected to. That's pretty deep. You cannot see the hardware address of the device you're trying to reach. If you're trying to send something to google.com's IP address, you will never learn the hardware address of the device that's going to pick that frame up and take it inside of Google. It'll never happen. It's very LAN specific. So if A wants to send something to B and he doesn't know where to send the Ethernet frame, and the Ethernet frame insists on having a destination MAC address, he's going to have to figure out what it is. How's he going to do that? He's going to broadcast out a message for help. It'll be an ARP query, and it'll say, I'm trying to reach this computer B. I don't know who he is, so I'm going to send it out to all the hardware addresses on this LAN, so every piece of hardware will pick it up. Every piece of hardware has to be able to run the ARP protocol. It's required. Printers, electric doorknobs, thermostats, washing machines, computers, etc. They all have to be able to run ARP. And I will send something out to all the MAC addresses, and everyone will pick it up. Everyone will look at it. They will all hand it to their ARP software, and their ARP software will immediately see that I'm trying to learn how to get to this IP address B. And hopefully there's a router on my network who knows how to do that. And he will respond with his own hardware address, thereby telling me I can reach B. I may or may not be that person you're looking for. And, I may be your destination, but probably not. But it doesn't matter. Just send me the packet, and I'll take it from there. So you will build an Ethernet frame with that device's hardware address, and the hardware address will then get it into the Mac, and it'll take from there. So you don't have to program where people are. Just listen for a minute. That's why they say ARP is plug and play. So I'm going to send something from A to B via, there's a router in the middle. So I know I'm going to end up on two different LANs. There's a LAN on the left and a LAN on the right. And I have IP addresses above and MAC addresses down below. So to send something from A to B, if I know B's IP address, then I'm going to build an IP datagram and say it's coming from all ones going to all twos. And I'll send it out on the wire. I don't know B's MAC address. So I'm going to send a broadcast out. I can't continue on where I'm at right now. But if I knew the hardware address, where I would send this would be to the router. But if I have to use ARP, I'm going to have to broadcast out so the router can tell me, here's my hardware address. It's the one shown in red in this diagram. So once I know the MAC address of the device that's going to help me, it's not going to be B's hardware address. It'll be the router's on this side on my LAN. And so I will build an Ethernet frame, and it'll get sent across the network. Once it gets inside the router, it's no longer on that LAN. So it leaves the LAN and sheds its MAC address skin. It sheds its Ethernet header. And I'm left just with the IP datagram. I look at my routing table. I consult where I should send it. It tells me send it out over the port on the right. That'll get it to B. And I build a new Ethernet frame to carry this same IP datagram the very last bit of its journey. And so this time what I'm going to put in the Ethernet header is a different MAC source and destination address. The MAC source address is that of the router, but it's this time of the port on the right, the one that connects to my LAN over here. And the destination address for this MAC is one it learned from using ARP. And it learned that the MAC address ended in 2A. And that's what you see in that diagram. All right, continuing on a little bit here. When you forward it over to B, B receives it, he throws the wrappers away, and you basically get your data out at the end. And if you want to see some more examples, and I'll give you some, you can actually go to this website. It's the same thing that we've done 100 times before. And maybe this one? Nope. It's got to be in the other page. maybe this. Yep, this is it. So this shows you a bunch of points, red dots. They just are places where I'm going to ask you what's going on here. And I've got some addresses I've given to the devices around the network. And in this case, I want to go from D to B, because that's what it says in the paragraph below the picture. And that'll change every time, along with the numbers and everything else. So if D to B, that's where I want to send stuff. Tell me what the contents of the Ethernet header and the IP header are at the following 3 points. So let's do one. Will be our last thing to do for today. We're going to go D to B, and we want to go 543. So D to B, so from here to here, and they want to know at 0.5. So at 0.5, I'm going to see source IP ending in 84, destination IP ending in Bs, which is 229, and that's IP. For MAC, the source address is going to end in 2B, and the destination address is going to be the MAC address of the router, because that's as far as I can go in the direction of B on my LAN. So it's going to be between these two devices here. And his hardware address ends in BC. These do not belong to the same device. That's perfectly okay. At 0.5 and 4, it's the same. So there's no point in answering 4. The switch changes nothing. When it goes through the router and I'm at 0.3, my IP source is going to be still D. So he knows who's it's coming from. Why would I change that? The destination address is still going to be B. That's how he's going to know it's for him. But on the MAC side, the source address is now this router port here. So it's going to be the MAC address that ends in 20, and the destination MAC address, it will learn from ARP, it will be DD. So I'll give you a chance to play with that too. All right, guys, that's all we have time for today. Thank you very much for your patience. Have a great weekend, and I'll see you back on Monday. Bye, everybody. Let me see the chat. I answered that one. Okay, good.